time looking at on chiller plant control. Always err on the side of too much water, okay? Chillers are always fine with too much water. They get very angry with low water flow.
Hey, Tony,
Yeah,
you're on bypass valve control right now.
Yep.
I've noticed when we do stuff, it seems like we don't put a fast enough acting bypass valve in.
okay.
I've seen that a lot.
Mm-hmm.
When we do have a fast acting bypass valve, it works great.
Mm-hmm.
But it's even trickier when we have just a regular 122nd.
Mm-hmm.
Why don't we always have a fast acting actuator on a bypass
Two reasons. One is it's not available,
for the size?
yeah, and the other is cost, okay? For a long time, you couldn't get fast-acting bypass valves from Belimo. You could only get them from Bray,
Right.
okay? And, you know, you were paying about twice as much. And if you get the other parts of the control okay, you're fine, you know, with a 90 or 122nd valve.
Because I've struggled with that. It seems like if we just paid a little more for the valve, it would take my startup and the trips. It just would be better to me. I think it would be money well spent.
Okay, and that's a valid point.
Also with isolation valves, we used to get them where we could adjust the timing on them. Is that still available?
Depends on the valve,
Okay.
on the manufacturer, yeah. We're gonna kind of get into a little bit of that here. On the bypass valve control, as Kevin just said, speed is vital, and it must be fast acting. Because when that chiller starts sensing it's getting low on flow, you want to get that bypass valve open and get some more water coming back quickly. Because especially if the load out in the system is dropping or is increasing rapidly, you could end up with a situation where you don't have enough flow. The set point for that bypass valve is vital. We all know that we have a chiller minimum flow set point, which is usually in the catalog and on the drawings, okay? But as we all know, if you use that set point for a DDC loop, what happens to a DDC loop? It does this, right? So if you have the set point at the minimum flow, the first time that DDC loop does this, you're going to lose the chiller. It's going to go off on minimum flow. Okay? So our rule of thumb is we will take whatever DP is required for minimum flow, and we will up that 20%. And that's what you'll usually see on your drawings for a set point. So that set point you see on your drawings is not the minimum flow for the chiller, it's the bypass valve minimum flow. And our goal is that we would never see it go below the 20% below that where we would lose the chiller. Open versus closed speed. This is one thing you can do something with. It's okay to have it close slowly, okay? Because that's just reducing flow. But when the chillers need flow, it has to open fast, okay? Are most of you guys familiar with adjusting the P with some logic on your DDC loops? I mean, usually you have a constant that's your P that you'll bring out as an AV or something like that. But what I've done on jobs that are really critical is I'll take that value and I'll run it through a logic block down at the PID loop. And I'll say, if the pressure right now is below set point, I'll take that value and multiply it by 2. And I'll say, I want this loop to act twice as fast if the pressure gets below set point. Okay? And then if the pressure gets above set point, I remove it and it works on the normal one. But that's one of the ways you can kind of force a loop to act at different speeds in different modes. Okay? Now we're going to talk about the chiller isolation valves. number one, try to always let the chiller control the valve, because the chiller is going to open and close the valve when it is given a start command and it's ready to start. So you don't have to worry about timing between when you send it a signal, and especially if you've got a UC 600 controlling the valve, and you've got chiller plant control, you've got the timing to get the control out to the 600, you got the timing of the 600, and then you've got the issue of when the chiller plant is going to do its thing. So it's best if you can try to let the chiller control the valve. Now, I said keep the valve open close time slow. Why do you want it slow?
Give it time to react. You don't
Right.
shock the system.
Yeah. When you think about we're running one chiller and we want to bring on a second chiller. So I've got established flow through here. Now, as soon as I start cracking that valve open, this DP will see it, and that DP should speed up the pumps, okay? But it's important that this guy have time to react while this one is moving. Now, if we make this valve real slow, it gives the system lots of time to react. So it only steals a little bit of water, the pumps speed up and everything works really good. Now, what happens if I make that a 10-minute valve? And I have a stroke time of 10 minutes on
Chiller is just to have a full, it doesn't see flow in time.
it. Right. The big key there is you have to keep it under the flow loss timer within the chiller. I think usually those are what, 2 minutes or 5 minutes?
So I think it's like 5 minutes.
So these things, the other thing is when you're shutting the system off. If you slam that thing closed immediately, it's going to have a big effect on the system.
Hammer it.
Yeah. If you just modulate it closed slowly, it works much better. Hey Jake, one thing that came up that Kevin was talking about was why don't we use faster acting actuators on the bypass valve?
Yeah, so right now, there's really two main options that we go with. It's the SR or the MFT. The MFT can be programmed for, I believe, 8-second drive time or 10-second drive time on the low end. The SR, I think, standard is 90-second drive time. The SR tends to be simpler on the install side. 90 seconds might not be fast enough. We haven't really discussed that, I don't know.
I was going to say, I think if we can, I know that the Bray valve, you can order it in different stroke times, okay? I thought about, can we get big MFTs? Do they do MFTs in the industrial actuators on Belimo?
The PR
Yes.
is an MFT.
Okay,
And that's the up to, what, 14, 16 inch?
Okay.
Yeah, it goes.
that's great. I would say that's a great takeaway. Let's look at changing our standard for the bypass valve to an MFT actuator. So,
That's an easy change.
yeah,
I was really not putting too much thought in it because I was sticking with what was simpler.
Yeah.
The MFT just adds complexity where it's like,
the big
24
thing,
volts, 2 to 10 ground versus why do I have 15 terminals?
but the big thing is the MFT, we can't adjust the stroke time on it.
With your phone.
Can you order it with the stroke time?
There are custom configurations you can get on
Because I would recommend that too, because we all don't have a tool.
Right.
Sometimes it's hard to.
Yeah, you do. On the PR, you do. Actually, no, on all MFTs pretty soon. For right now, just your just the PR MFTs though, you can download their app, and your phone uses NFC to connect to it. You just pop it on top of the
Really?
actuator.
Yeah,
Yeah,
if you guys,
Nate and Kevin actually got to see it.
if you guys haven't seen that yet, it's kind of like, the airflow stations you've
Right.
seen?
So it's like it's Bluetooth in a sense?
Yeah, Belimo's done the same thing
Oh, that was
with their more expensive actuators. They've got near field on them.
It is. It is going to be long-term, it will
Sure.
be added to all MFTs, but for right now, it's only the PRs, but those are the bigger ones anyway, so.
That would be great, yeah.
They are
I haven't
awesome.
seen that yet. Because, I mean, I've done it with the Evtrons.
The bad part is it is NFC, and I have not had the best luck getting it to connect without basically physical contact on the actuator.
Yes.
Which, if the actuator's upside down, then you're holding it like this.
Called duct tape.
Yeah, it's,
You would never install the actuator upside down.
Should-
I wouldn't, I don't install it.
Why wouldn't you install it upside down, Jake?
What, an actuator? Why wouldn't I? I don't know. Why wouldn't I?
Drippage.
Oh, because then you could flood the actual actuator if it had a leak.
Yeah, if you got a leak in the valves, a stem leaks or something like that, then you flood the electronics with water. And that's why any electronic actuator, if you look at the installation manual, they'll always tell you that it has to be installed at the horizontal or above. And that's just simply so if a leak springs, you don't blow up the
It
actuator.
should be always.
Yeah.
Yeah, because if it leaks,
That
the
is-
one thing to worry about is the actuator.
If not, they should move it.
Yep. Okay. Chiller isolation valve, always let the control valve, the chiller control the valve, keep the valve open and close time slow. Turn on the pump before you open the valve. Okay, if you turn on the pump before you open the valve, think about it, on our valve control. This chiller is running and the VFD is at 80% speed. When we turn on a second pump, what speed do we normally turn it on at?
20%.
Well, but as soon as it's ready to run, we match pump speeds. You always run your pumps at the same speed. So that pump is gonna go up to 80% as soon as we start it. And the good news is, that's what we want. We got lots of head available at that valve. That pump's working hard. So as soon as we start cracking the valve, we're gonna have good flow everywhere. So that's why you wanna get the pump open, the pump going. And again, make sure the operator is slow.
Hey, Tony, when we don't do it on centrifugals where we don't take the pump output. You usually do that on the RTAs, correct? I mean,
Say that again?
on centrifugals, we are not taking the pump output and bringing it to our 600. You know, a lot of chillers will take the pump output.
Oh, I know what you're talking about now, I'm sorry.
On
Yes,
centrifugals, I don't think we do that normally, do we?
no. There are some
Just
chillers that Trane company manufacturers, that they're all air-cooled machines, that due to the design of the evaporators, if the ambient temperature changes quickly, you can get refrigerant where you don't want it, and you could conceivably freeze up the evaporator. And on those kinds of chillers, they require that the pump be able to run anytime, whether the chiller's enabled or not. And in that case, the pump output is wired from the chiller to the pump. So that if you get one of these ambient conditions where the refrigerant migrates, the pump starts and it keeps from freezing the evaporator.
Or it gets wired to our 600.
We have an agreement with the service company that if we have staged pumps where we can't do that, that pump output will wire to a UC 600 as an input, and we will have programming, standalone programming in that 600 to make sure a pump starts whenever that thing requests it.
But what I want to say is if you see a centrifugal, don't have the centrifugal control as well.
Yeah, you don't, traditionally the centrifugals, the pump output will control the valve.
Correct.
Okay, last math question before lunch. This has to do with adding and subtracting logic in chiller plant control. Now, chiller plant control has one mission in life. I need to make water leaving that plant at a temperature. That's my primary goal. And no matter what's going on with bypass lines and everything else, my goal is that the system sensor, I'm going to maintain that at set point. Now, what logic do we usually use to add chillers in chiller plant control?
Oh, system temperature. temperature or,
To add is just temp.
temperature.
Temperature and
Differential
time.
time, oh, yeah.
Okay? In chiller plant control, what it normally uses to add chillers is you have to be so many degrees above set point for a period of time. And after that, it will throw up the add flag and it will add the next chiller. Okay? That's pretty straightforward. Okay? Now, some people will tell you that you should have in there a permissive that says, oh yes, and the running chiller has to be at least 95% loaded, because you don't want to start up a second chiller if the first one's not doing the work. Okay? Does anybody know of a drawback to that?
Well, if the chiller's not performing, the way we do, we have it designed,
Our chillers have adaptive controls on them. So let's say the tower fan's not working real well, okay, and the condenser pressure starts getting high. Well, the running chiller is gonna automatically unload the chiller to try to keep it online. And so it's not going to be at full load current, but we need more cooling in the building, okay? So some specs require it. If they require it, we put it in. But I don't think it's good from an operating standpoint to use that as criteria for adding a chiller. Now, what we're looking at here is I'm saying we have a system delta T of 10 degrees. And in chiller plant control, you have to tell it what's the system design delta T, what's the subtract deadband. And then you have to give it the chiller size so it can calculate what's going on. So I have a system that was running under pretty heavy load. I had 2 chillers running. And right now, both chillers are running at 30% load. The system supply is 42. The system return is 51. And the customer's going, what's the matter with your chiller plant control program? I'm running 2 chillers at 30% load. I don't need that second chiller running. That's not efficient. What do I want to do? Does anybody know why the system won't shut off the lag chiller?
I mean, there is a delay, but
Okay,
if it won't shut off at all.
won't shut off at all.
Because we're not more than 2 degrees delta for the subtraction deadband.
The way that chiller plant control does is, first of all, it says I have equal size chillers. So that means theoretically, each chiller can do, of the total system work, can do 5 degrees worth of work. Okay, because if 2 chillers are doing 10 degrees, 1 chiller can do 5 degrees. And we told it has a 2-degree deadband. Well, if 1 chiller can do 5 degrees, it looks at the return water and says, okay, the return water is 47 minus 2 degrees, it has to get below 45. So until we get below 45 degrees, it won't shut off a chiller. Now, the reason I bring this up to you guys is one of the most common complaints we have on chiller plant control is after we've had a peak and we've got multiple chillers running, the lag chiller doesn't want to turn off. Okay? And that's always because of this number and this number. And what I've found is that most of the time the design engineers are wrong on their delta T. They design the system on 10 degrees, but a lot of times they operate at like 8 degrees. And so you'll never get the delta T you need to get it to turn off. See, the return has to be below 52 minus 5, and that fraction of that 5 comes from the percentage of load you want to turn off. I'm saying you want to turn off a 500-ton chiller and you've got 1,000 tons available, minus 2, or less than 45. Okay, this is the hardest question you'll get. Oh, wait a minute, no, I got one harder than this, I'm sorry. Hey, what time did you order lunch?
Right there.
Did I?
Yeah.
No?
Is the office providing lunch today?
Yes.
Do we know when?
We're tacking on to services lunch,
Okay,
so 11:30-ish.
okay, good. That'll be right when I finish this first session. Okay, I have a 16-degree delta T. Subtract deadband is 2 degrees. I have equal size chillers. Supply system is 42. At what return temperature will the lag chiller shut down? I should have done a multiple choice answer on this one. I didn't.
You got a whiteboard.
What's that?
You got a whiteboard.
Would you like multiple choice?
I'm sorry, you couldn't hear me. I said white.
Okay, you have multiple choice.
Hey,
So, system design is 16 degrees of deadband.
Subtract.
Oh, subtract.
If I have equal size chillers, each chiller is going to do how much of that 16-degree work?
8.
Okay? So that means if I have a 16-degree delta T, I'm going 58 down to 42, right? So now half of that, if I got an 8-degree, did I do that for 42 or 44? Half of that is going to be, the first chiller is going to go 58 to 50, and the second will do 50 to 48. Okay? And, I'm sorry. Yes. So theoretically, at 50-degree return, one chiller can handle it, but I told it we have a 2-degree subtract deadband. Okay? What's the right answer?
A.
A. I purposely didn't make it C that time.
I just figured you put the first answer the right one, so you remembered to put the right answer.
Okay, now this is the hardest one you're gonna get, and it's the last question before lunch. I have a system delta T of 15 degrees. I have a subtract deadband of 2 degrees. I have a 1,000-ton chiller and a 500-ton chiller. At what return temperature will the 500-ton chiller shut off? Okay. I'm not gonna give you multiple choice.
What's a retro?
I'm sorry?
What's a retro? The retro temperature.
Oh, the red run?
Yeah.
when my dyslexia kicks in when I'm typing.
Right.
Yeah, every single slide.
That's too much math.
Hospital? Yeah, hospital.
Okay, let's do the math.
Looking at it.
I got a 15-degree delta T, right? How much work will the 500-ton chiller do?
5.
5 degrees. How much work will the 1,000-ton chiller do? Be 10 degrees. Okay, now I've decided in my chiller sequencing, this is the one I want to turn off. So I've got 15 degrees and 42. $57, right? Okay, if I want to turn off this chiller, I got to take off 5 degrees, that's 52, okay? And then I got a 2-degree deadband. So at 50 degrees return water, I'll turn off the lag chiller. Does that make sense? All right. Now let's change the math. What happens if I decide I want to turn off the 1,000-ton chiller and I'm running 1,500? What does the return water have to be then? Okay. So we take 57 minus 10 minus 2 is 45 degrees. So if we want to turn off that 1,000-ton chiller, we got to wait till that return water gets all the way down there. Okay? Now, probably 80% of our multiple chiller jobs have equal-sized machines, so it's not a big deal. But when we get into bigger chiller plants, a lot of times you will have the ability to do that.
Where would you see this type of system?
Where have we seen unequal-sized chillers? We've got, I know Romeoville hospitals, a lot of hospitals do.
Community college and community college, they got a bunch of different kinds.
Okay?
Would you consider that with Albany's, where they have that swing cooling chiller? Because they have the heat recovery.
No, that's really a different deal there.
Yeah.
Because of the application. I'm sorry?
Maze Lake Retirement, I think that retirement village has got a small one and a big one.
Yeah. I can't remember why we did that.
It's because we had a spare little one that we needed to use.
We had a little, this is being recorded. We needed to get rid of it. Yeah,
Backstop, backstop.
A lot of manufacturing, Tony, process control.
Yeah.
So they can run a machine, you know, in cold weather, cooler weather.
Okay, how's your head? I think this would be a great place to take a break for lunch. Any questions? I want you guys to be systems people.
It's his dying wish.
All right, let's eat lunch. Okay. Nothing is more fun than real life lessons. So I'm going to invite Mr. Cutts up to explain something. This was a project he was on where we had a couple of boilers. It was actually a variable primary system. We have this out here, and they put in a flow meter, and Kevin had some DDC loops running to maintain different flow rates depending on how many boilers are running. And they obviously had to put in a bypass valve for it. So they put in a bypass valve.
Yeah, Tony was out there doing his quality audit, and the system just wasn't quite working right. We checked the mechanicals, I did, and it was piped exactly, I could show it on the mechanicals. But what it should have been done which, correct me if I'm wrong, Tony, wasn't it this,
Yep.
like this? But even mechanical showed it, and once, then we called Acitelli, and Acitelli got an extra by the engineer to come and to correct it. But just so you know, even though the mechanicals may show it, it's not always right.
And what you need to do is when you see something like this, take your thing to extremes. Okay? What happens? When this valve is completely closed, what happens?
Water flows through the boilers.
All the water has to go through the boilers. Okay? When this thing starts opening, where does the water go?
Through the bypass. Instead of
Okay. What happens is we just created a loop right here. You see that? And Kevin's DDC loop was doing a good job maintaining minimum flow. However, the minimum flow it was controlling was maximum flow. So in other words, these, let's say these were like 80 GPM. And every time these boilers would go above 80 GPM, the bypass would open up a little bit, and they'd stay at 80 GPM. Everybody see that? And the only way to fix that is you gotta take the water under the high pressure that's headed back to the system and connect it back to the inlet of the boilers that way. So now it's pushing water this way, okay? And so now the water goes like this when you open the valve. And now you can maintain minimum flow on the boilers. But before we couldn't maintain minimum flow. Okay? And Kevin was right, they had two different flow diagrams on the drawings. You know, the mechanical layout for the room had it piped this way. And that's what the pipe fitter went off of. But later on in the drawings, in the temperature control side of the mechanical drawings, there were schematics. And in that schematic, it was shown this way. So I'm really surprised he got paid an extra. Normally they wouldn't get paid if it's right on one of the drawings.
Yeah, they got paid. They worked that night, and I went out there and gave them a hand.
Okay, did we get an extra? Okay,
You got a very good job. Thank you very much, Mr. Perkins.
how many of you guys like rules of thumb? Okay, I think everybody likes rules of thumb. So the next 5 minutes is going to be rules of thumb.
That's what estimating is.
Huh?
That's what estimating is.
Yeah, that's what estimating is, right. Okay, let's talk about air delta T. Most systems, what temperature supply air do we provide? 55. I gave you the answer to this. In Chicago, what's our normal mixed air temperature?
80.
80, okay? So, for most systems, this is what we would expect to normally see on a cooling coil, all right? Now, I think almost everybody in this room has been involved in a job, actually two of them. Does anybody know what happens when you send colder than 55-degree air to a space? Why do we stop at 55?
Condensation issues?
Hmm?
Is it condensate issues?
Yep, it can be condensate. When the air is colder than 55, you need more insulation on the duct to keep it from sweating. But the big thing is, when air drops out of a diffuser onto someone, ASHRAE a long time ago did a lot of comfort studies. And they found that when that air is colder than 48 degrees, people perceive that as being uncomfortable. It's a cold draft, okay? Now, does anybody know what jobs we have in Chicago that supply 48-degree supply air?
AT&T.
You ought to know.
Boeing.
Huh?
Boeing.
No, not Boeing, it's the only one that doesn't.
500.
500 and NBC were both designed, the air handlers put out 48-degree air. And you go, how the heck can you provide 48-degree air and the people don't feel you're freezing? Well, the answer is, we have fan-powered VAV down there. And we have a primary air damper here, which has 48-degree air. And what we do is, this is the only job you'll ever see this way. This fan will be designed at maybe 1,000 CFM, and the primary air will never go over 800. Okay? And the reason being is, this pulls 200 CFM of plenum air in here to mix with this to get it up to 55, so we don't send cold air down the duct. All right? Now, you might ask, why do you do 48-degree air? Well, everything is based on delta T. So if I have 48-degree air, the amount of CFM I have to send is substantially less. So your supply ducts get smaller. That helps in the plenum space in the buildings where they're putting ductwork in because you're using smaller ductwork. So that's why you use cold air. Okay. Let's see, hot water. What are most systems designed at for supply hot water temperature?
120 to 180.
Okay, 180 is usually the design, pretty much. Does anybody know what kind of delta T's they're designed on?
30 degrees.
20.
30 to 40.
Do I hear any other votes? First of all, everybody's right. There's really 3 different designs you'll see. One is a 20, one is a 30, and one is a 40. Okay? And all that means is the boiler should be on a 180-degree system, it's designed at 180 in and 160 return. If you've got a 40-degree system, it's designed at 180 in and 40 out. And the real easy way to know that is you go look at any submittal on a piece of heating equipment and see what the delta T is on it.
180 return
No, supply.
and then 140 return.
Yeah. This would be 160 return, this would be 150 return, and this would be 140 return.
You're
Okay?
talking system, right, Tony?
On the system. And sometimes they'll design some equipment at 20 degrees and some other equipment at 40 degrees. Okay. Chilled water. What's the most common leaving water temperature design?
44.
Okay. 40 to 44 is the most common. What's the most common delta T?
10.
Now, I'm going to blow this one up in a few minutes here, but that's pretty much standard. On the condenser water on a chiller, when you have a cooling tower, what are they normally designed at?
80.
Anybody know? Normally they were also 10. And those would be 85 to 95 typically. Okay, another easy one. You're looking at an air handler, and you have no idea how many CFM that air handler is. Okay? And you want to make a guess at it. Okay? Cooling coils are all designed right around 500 feet per minute face velocity. Okay? Does anybody know how to tell how many square feet a Trane air handler is? If you're looking at it? Model number. When you look at a model number and it says CCAH52, that means that unit has, the nominal coil size is 52 square feet. So if you take 52 square feet times 500 feet per minute, you can say, hey, that thing's about 26,000 CFM. Okay? On other Trane equipment, do you know how to tell on a Voyager what the tonnage is?
Wait, can you say that again? How can you tell square feet of a Trane air handler again?
Model number.
Model number?
It'll have-
Which number?
It's usually 4 letters,
4 letters?
like MCCA was the old model, modular climate changers. Now they're what,
CC something.
CSA.
CS?
CS.
CSAA?
4 letters, something like that.
But after the 4 letters, there'll be 3 numbers. And if it's like 012, that means it's 12 square feet. If it's 063, it means it's 63 square feet. Okay? You know how to tell the tonnage of a Voyager rooftop?
It's a model number 2, isn't it?
Okay? What does the model number say?
It goes by basically 12, like the tonnage, or like the BTUs, right? So like multiples of 12, 12, 24.
Yeah. The important thing is those are MVH. So like if you see a YCD and it says 06, or it says 600 on it, that doesn't mean it's a 60 ton. It means it's 600,000 BTUs, which means it's a 50 ton. Okay? Once you move to IntelliPacks are all tonnage. So like if you see an SFHA 50, that means it's a 50 ton. Okay, so you've got an air handler and you figured out how many CFM it is, and now you want to know how many tons it is. Okay? Usually about 400 CFM a ton. Okay? Now the thing you need to know about all of these numbers is you can't absolutely apply all of these all the time. These are what are called rules of thumb, they'll get you close. All right? The things that really throw these off are different things like 400 CFM a ton is fine for a packaged rooftop that's handling 15% outside air. Okay, but we've all seen like the KCC makeup air units. You know what those things run, CFM per ton? Well, obviously, if we have to cool the air from 95 down to 55, it's going to be a lot more cooling for that CFM. But typically, a makeup air unit will run around 200 CFM a ton. So if you're looking at a KCC unit, don't think that it's, you know, your CFM numbers are different on those. Okay? So those are just a bunch of rules of thumb if you're just trying to get close on something and you want to know. All right. The next thing here is a presentation I gave to a group of people a couple of years ago about chilled water system optimization. Okay? And we talked earlier over there about a 10-degree delta T on the chilled water and a 10-degree on the condenser water. Those are very, very, very old school numbers, and we shouldn't be using them today for good design. Okay? But for this presentation, we're talking about what do we want to optimize on a given building. Do you want to minimize the tower fan KW? We're looking at just chilled water systems here. Do you want to minimize the condenser pump KW? Do you want to minimize the evaporator pump KW? Or do you want to minimize the chiller compressor KW? Which one of those do you want to minimize?
All of the above.
That is the right answer. The answer is all of the above. The thing we have to be careful of is especially equipment vendors will focus on the thing that they have the most effect on, okay? So a guy will tell you, well, my chiller can get down to 0.38 kW per ton. Yeah, but he doesn't tell you that, you know, his GPM is gonna be twice what everybody else's is, so that pump KW is gonna go way higher, okay? And the key to this is, the electric meter is on the building, okay? If you save money in one part of your system and it costs you more somewhere else, you didn't save that money, okay? Because the meter is on the building, the meter isn't on individual pieces of equipment. So this focuses on how we can try to save some money. This is a real interesting thing. It's called the chiller COP, the coefficient of performance, which is a function of chiller efficiency. And back in 1977, you were hard pressed to get a 4 COP. Now we're up on some of them over 6.5, okay? And how did we get our efficiencies on our chillers up so dramatically? The main thing is the tubes. Back in 1977, the tubes in both the evaporators and the condensers were smooth bore tubes, and the external side of them was smooth also. And there is a theoretical limit of how much heat transfer you can put through there. Then somebody got the brainy idea of, if we put rifling inside the tube, it'll increase its heat transfer. And if we put fins on the outside of the tube, it will increase heat transfer. And that drove about 75% of the energy savings, was putting more tubes and more efficient tubes in chillers, okay? Now, if all it is putting tubes in chillers that makes them efficient, why don't we make them all really efficient?
Cost of manufacturing.
Cost of manufacturing. Copper is an expensive material. So the more tubes you put in the chiller, the more expensive it is, but the more expensive it is to manufacture. Okay? So it's always balancing cost versus performance. Now the other thing is compressor design has changed fairly radically. And compressors are more efficient now. Trane has a 3-stage compressor, which is a little more efficient than a 2-stage compressor. So there's other reasons. But over the years, the chillers themselves have become much more efficient. So they're saying it's improved 58% since then. Now these are the rules of thumb I had over here. 44-degree chill water, 10-degree delta T, what's called 3 GPM for condenser flow, which is a 10-degree condenser flow. And the question is, should we be using those today? In some studies that were done by Ashray and another guy called, another study from a company called Kelly and Chan, they're saying chilled water should be anywhere from 12 to 20 degrees. They're saying 18-degree delta T. And condenser water should be from 12 to 18, and they're saying 14. Now, when we reduce our flow through the chiller, what energy savings do we get? Where does the energy savings come from?
Heat transfer.
No, not heat,
Pump speed.
pump energy. Right, when we lower the flow, the pump energy goes way down, okay? So we're saving pump energy here. Now what we're trying to say here is that if we look at our kW per ton per year at 4 different leaving chilled water temperatures and 4 different delta T's, you can see what our energy is. Okay? Now we said our rule of thumb was 44 degree leaving water and a 10 degree delta T. You can see that the compressor energy is pretty good here. The chiller energy is pretty good. But our pump energy is real big. And as we keep changing this, and by the way, the reason we provide colder water is to keep that log mean temperature difference the same in the coils, so we don't have to change the coils. If we go clear down here to 41 degrees and a 16 degree delta T, that uses less energy than this. So that's a good one. That's a good reason to run higher delta T's on our system. They suggest that it never makes sense to use the traditional 10 or 12 degrees that are commonly used. So anytime you see a system designed that way, the engineer is typically has taken something that he's done before and he's regurgitating it for another job rather than do more design work. It says if life cycle costs were minimized at the largest of the 3 delta T's, about 15 degrees for the condenser water, and that's 2 GPM instead of 3 GPM per ton, and that means 67% of the flow, which is 0.6 times 0.6 times 0.6 for energy savings. Okay, so you can see there's a lot of energy to be saved there. So in the past, the chilled water was 2.4 GPM per ton at a 10 degree delta T. And we're trying to move that to 1.5 GPM at 16. Condenser water used to be 3 GPM per ton at 9 or 10 degrees. And we're trying to get that to 2 GPM. And those flows will result in a more efficient system than what we're doing now. You guys are all probably, have you all worked on some job with a cooling tower? Not yet. Okay. Cooling towers, you send water over the tower and you blow a big fan through that water and it evaporates water and it cools it down so it can come back to the chiller. Cooling towers, since they're an evaporative function, they work on what's called the wet bulb temperature instead of the dry bulb. Okay? A regular air-cooled piece of equipment, the amount of heat it can reject is directly proportional to the temperature of the air coming into the coil. On a cooling tower, they work off the wet bulb temperature, which is a little lower temperature. And when it's dry outside, it's a lot lower. Now this is just some basic design information that we're using for the basis of the study here. With 85 degree entering condenser, 10 degree temperature differences on evaporator and condenser. What we're going to do is we're going to look at the effect of different flows on kW. And here at a 2.4 and a 3, which is our baseline old design, it's 281 kW. If we go to 1.5 degrees on the evaporator and 3 degrees on the condenser, it drops our kW down to 276. You can see here if we go to 2.4 and 2, it's 278, so you don't get quite as much savings there. Reducing both chilled water and condenser flow rates, you can optimize it and end up where they are there. And this just talks about the tower kW, the condenser pump kW, and the chilled water pump. And you can see here at our original design of 10 degrees on both systems, you've got that. And when you go low flow, this shows the kind of energy consumption you can save. And this has to do with the load in the system. So before, everything I was showing you was at 100% load, at full load. At part load, it even gets more savings. Let's see, I think that's it. Variable primary flow. Okay, we talked about that this morning. Condenser water set point is one you'll get into fights with the service company over. Engineers want the coldest condenser water possible because that's the most energy saving. Chiller manufacturers don't like, especially the startup guys, don't like cold water because it can be harder to get the machine going with really cold water. It's tough to get the oil moving. So in our case, all our machines are published down to 55 degrees that they'll start and run at low load there. Now here's what we're saying is that when our condenser water is 72 degrees, the chiller's really efficient, okay? So it's got cold water coming in. As the water temperature comes up, the chiller uses more energy, which makes sense because it's doing more work. Now you look at the tower, and down here at 72 degree tower, I'm running the tower fans wide open and moving a lot of air, which is taking a lot of horsepower. As it gets hotter out, it takes less horsepower because I'm not doing as much work. So when you put all that together, you get this. And you can see at real cold tower water, it costs you a lot to operate. But this comes down, and at some point, there's a low point, and then it starts going up. So there is an optimal tower temperature to run. And if any of you guys ever used the Trane condenser water optimization routine, Trane company actually has one built for you. It's a TGP2 routine, and it will calculate that.
That's in the configurator too, isn't it?
Is it?
I think so.
I think
Yeah,
it
I think it
is.
is now.
So they're saying with optimized tower water, you can save up to 5% of your annual energy consumption if you optimize it. And last slide, when you're talking energy efficiency, just remember the meter is on the building, it's not on a piece of equipment. So optimizing one piece of equipment may end up costing you more in the long run. So you gotta remember to look at the whole system. Okay, where's Eric? I'm done. Where's Eric?
Thanks, Tony.
Any questions on any of this?
Hey, Tony, you want to talk about one of the flags that I was talking to you about on Kishwaukee is when you have 100% outside air, you know what to look for? Take the flag.
What's that now?
Out of Kishwaukee, do a flag, because a lot of times we have units that are 100% outside air,
Okay.
and what should they look for? Like what I asked you for the coil size?
Oh,
'Cause I mean, stuff like that is, I know, sometimes they'll put a blower coil in, and it's really not rated for outside air, but they should keep an eye on it.
oh, okay. Well, out at Kishwaukee, Kevin had a fan coil. And it was 100% outside air. And he was worried, you know, fan coils, they shouldn't be able to handle 100% outside air. They're not designed for it. Fan coils usually have 2 or 3 row cooling coils in them, you know, they're real small, and that won't work. What we actually had here, and this is kind of a naming thing, we called it a fan coil because it was using a UC400 with a configuration file in it for a fan coil. But in fact, the piece of equipment here, what they bought, was what Trane calls a blower coil. And a blower coil is actually a mini air handling unit. And what they had done was they had put, I think it was an 8 row coil in the blower coil so that it could handle 100% outside air. But when you guys are questioning whether the piece of equipment you have may be correct or not, the first place I'd go is to the BoxNet account, go to the job folder, go to the engineering folder, and now every piece of equipment that we have information on when we do the design drawings, we put that equipment in the engineering folder. There's an equipment, there's Trane and non-Trane equipment. And you can hunt through there and find out all the information on the equipment. Now, I'm not gonna say that's always 100% correct, because sometimes there'll be a resubmittal that we don't get later on somebody's equipment, but it should get you in the ballpark to start with, if you got a question. Okay?